our final lesson in the discrete functions unit, and we kick it off with an investigation. A nickel is placed on a game board with 32 squares. So here we have one nickel. All right. On each succeeding square, the number of nickels is doubled. What does that mean? Well, if there's one here, then there's two here, and there's four there, and there's 8 there, and so on. Okay? How much money will be on the last square if we zigzag our way all the way through? How much money will be on the last square? And how much money will be on the whole board when it is full? So you can see that this is the sum of the terms of a geometric sequence. Okay, it's a geometric sequence because it is progressing by a common ratio, and it's a geometric series because we're finding the sum of all of those things. Anyways, let's work through this step by step. So we have our number of squares, and we're going to start with square number 1, and on square number 1 there is 1 nickel. Okay, well, how many total? 1. On square number 2 there are 1 times 2, so there are 2 nickels. How many total? Well, now there's the 2 on the second square plus the 1 on the first square. That's a total of 3. In the third square, our number doubles again from 2 to 4. In the fourth square, it doubles from 4 to 8. In the fifth square, we get doubled to 16. I'm going to do a few more here. From 6, on the sixth square, there are 32. And on the seventh square, there are 64 nickels. Now, let's think about the total number of nickels if we add the square that we're in and all the preceding squares. So if there are 4 on the third square, we really have 4 plus the 2 preceding. So it's 4 plus 3, actually, which gets us 7. And we're going to start to see a relationship. In the fourth, if we add up the total, we have the 8 that are on that square plus the 7 that went before it. Well, look at this. We have 8 plus 7 is 15. Sorry. In the next square, we have 16 plus the 15 that went before it. So you're starting to see a relationship. 15 plus 16, 31. 31 plus 32, 63. 63 plus 64, 127. Now we are being asked at the bottom of that chart there to develop a formula for the total number of nickels on the board and use this formula to calculate the total number of nickels on the game board. So what we're going to do is look for a pattern and look for things that we know. So something that we know is that a geometric sequence or series deals with a common ratio, which means that there's a number that's going to be multiplied by itself again and again in order to get each subsequent term in the series. Well, what is that common ratio? In this case, we're multiplying by 2, by 2, by 2, by 2, by 2, by 2. So the real question is, how many factors of 2 are there in order to help us get the total number of nickels? So that's your hint. You're using the standard formula for exponential functions, and you're thinking about, okay, the common ratio here, the common factor that I'm working on with is 2. Try that for a little bit. Pause it, try it, come back, check. All right, let's work through this together a little bit. I'm sure the pattern was pretty tough to see, but if you took the factor of 2 and you raised it to the power of 1, you would get 2. And then if you subtracted 1, you'd get 1. So 2 to the power of 1, subtract 1 is 1, okay? That sounds a bit funny right now, but let's see how we do it now. Let's take our factor of 2, And if we take 2 factors of 2, so if we raise it to the power of 2, we'll get 4. Now I realize that this should work straight across through here. But look at what happens when you subtract 1. Okay? What's 8 minus 1 is 7. And how do you get 8? Well, you take 3 factors of 2. Okay? 4 factors of 2 is 16. Take away 1, it's 15. And that's how you get from 4 straight to 15. 5 factors of 2, take away 1. 6 factors of 2, take away 1. And so on and so on. So the formula that we have here for our total number of nickels, which is the series, the sum of the terms up to the nth term, is as follows. We have our common ratio of 2. We're going to raise it to the nth power, and then we're going to take away 1. Okay? If you didn't get that, that's fine. That's why we're learning all this today. On the bottom of your page, you should have a little bit of space for notes. I'm just going to clear this. And we'll say geometric series. Geometric series. The indicated sum of the terms of a geometric sequence. The indicated sum of the terms of a geometric sequence. Essentially the same definition we worked with yesterday, but we sub out the word arithmetic with geometric. And again, the indicated sum, that's simply right here, this is saying take the sum of the first n terms, okay? So that's the symbol for indicated sum. So the sum of the first n terms of a geometric sequence, the sum of the first n terms of a geometric sequence is S sub n equals a, that's the first term. And what's the second term in a geometric sequence? Well, it's simply the first term times 1 factor of the common ratio. What is the third term? It's the original term, and now you've multiplied it by r twice. The third term, a times r to the power of 3, the fourth term. And it carries on like that until you get to the end. And the final term has how many factors of r? Well, the first term does not have any factors of r. So this, and then it counts up 1, 2, 3, 4, 5. So the last term must have 1 less factor of r than the number of terms. So it's to the power of n, which is the number of terms, take away 1. That's how many factors of r the last term has, because the first term doesn't have any. Okay? So let's derive a formula for S sub n, which is the sum of the first n terms. And we're going to do this the same way that we did, well, similar way than we did yesterday, okay? We're going to start with the definition or the formula for the sum of the first n terms, what we have here. In this case, in order to use this formula, you'd need to know every single term. Okay, so we're going to generate a formula that allows us to calculate the sum without knowing every single term, or sometimes even what, how many terms there are, or sometimes even what the common ratio is. Okay, so we're going to work through it like this. We've got a plus a times r plus ar squared. Skip a bunch in the middle until you get to the end of this sequence, whatever it is. The last term is going to be a to the power of r, a times r to the power of n minus 1. And what we're going to do to develop our formula here is we're going to multiply both sides by r and align like terms. So we're going to, I'm going to leave some space here, multiply both sides by r and align like terms. All right, so on the left side, if we multiply the left side by r, we end up with r times the sum of the first n terms. And if we multiply each of the terms on the right side by r, we take a and we multiply it by r, we end up with a times r. And I'm right away aligning like terms. Okay, so if I take a times r and I multiply by r, I end up with, I'm just going to skip the same spots because I'm aligning all these like terms. And as I get to the end of the formula, I have arn minus 2, but I've multiplied it by r, so I have arn minus 1. And then I have arn minus 1, and I'm going to multiply that by another r, and I'm just going to end up with ar to the power of n. Okay, so each term on the right side and each term on the left side has been multiplied by r, and then we lined up like terms. Now what we're going to do is we're going to take equation 1 and subtract it from equation 2. Okay? I'm going to take equation 2 and subtract equation 1. So on the left side here, I end up with r s sub n minus s sub n. And on the right side, if I'm doing 2 minus 1, well, this term take away that term, 0. This term take away that term, 0. All the terms in between here, take away these guys in 1, 0, because they all line up. This term here, take away this term, 0, leaving me with just positive ar to the power of n and negative a, right? Because here I have 0, take away a. So what I'm left with is negative a plus a times r to the power of n. Okay, and I'm going to just rearrange this right side because it looks a bit awkward. I'm just going to swap these two terms. So I start with a positive term. Okay, so we have a times r to the power of n minus a. Well, let's look further at this left side. What can we do in order to simplify it? And actually, we're going to use the same strategy on both sides. We're going to factor both sides. So here I see a common factor s sub n. So I factor that out, leaving me with r minus 1. Over here, I have a common factor of a. Factor that out, leaves me with r to the power of n minus 1. Well, now, in order to get the formula, to simplify it, I just need to divide both sides by r minus 1. Okay? So on the left, we're left with s sub n. Leave a little bit of space. And on the right, I'm going to have what I started with in the numerator. And we're going to divide it by r minus 1. And there is a restriction here because my denominator is not allowed to be 0. That would be undefined. R cannot be 1. So there we have it. This is the formula for determining the sum of the first n terms of a geometric sequence, geometric series. We're going to apply that in our examples. All right, working into it. slowly. In example 1, we're asked to identify if the series is geometric and then justify our answer. So what has to be true about the series in order for it to be geometric? Well, in order for it to be geometric, there needs to be a common ratio to get us from term to term. Okay, you can already see that there is, but we're going to show it. We're going to verify that using some simple algebra. So here we go. Arithmetic, really. To be a geometric series, comma, it must have a common ratio. So we take term 2, divide it by term 1, has to be consecutive terms. We get 3. Well, let's see if we get that ratio between term 3 and term 2. Yes. Let's try again, just in case. Take term 4, divide it by term 3, and we get 3. So there is a common ratio of consecutive terms. It's 3. Therefore, let's say r equals 3, comma, therefore, geometric. In B, we have the series 2 plus 8 minus 12 plus 16 minus ... So what are we going to check for? We're going to check for a common ratio. So we take consecutive terms and we divide them. 8 divided by 2. That is 4. Okay. Negative 12 divided by 8. That's negative 1.5. Doesn't look like this is going to work out. Let's try the last one. 16 over negative 12. In our calculus, sorry, negative 16. Nope, typo in the book. 16 divided by negative 12 is going to be negative 1.3 with a repeating decimal. No common ratio. Okay. The ratio of consecutive terms is not constant, no common ratio, therefore not geometric. Okay, you're simply looking for a common ratio. If it's there, it must be geometric. If it's not there, it can't be geometric. In example 2, we're asked to determine the sum of the first 10 terms, and they've given us the first term, and they've given us the common ratio. So all we need to do here is take our equation for the sum of the first n terms of a geometric series and sub in what we know. Okay, so we're going to sub a, which is the first term, a equals 20, r equals negative 3, and don't forget, we also know what n is. N is 10, because we're looking for the first 10 terms. So here is our general equation. The sum of the first n terms is equal to, in the numerator, a times r to the power of n, in brackets still minus 1, close bracket, and in the denominator, r minus 1. All right, so we're subbing in what we know. We're finding the sum of the first 10 terms. We've got an a of 20. We've got an r of negative 3. I'm going to keep that negative sign with the 3. Okay, this bracket is very important, especially if you're going to be working on your calculator. You need to bracket that negative sign. In this case, it ends up not mattering because 10 is, oh no, it matters very much because 10 is even. So this is going to come out as a positive. Minus 1, and looking to the denominator, we've got r of negative 3 and minus 1. All right, dealing with our brackets here. Negative 3 to the power of 10. Click it into your calculator, subtract 1. In the numerator, that leaves us with 20 times 59,048 over -4. Put that in your calculator, or end up with -5 times this number in the bracket, 59,048. You end up with the sum of the first 10 terms being -295,240. Okay? Again, that's just subbing in the information they gave us into our equation for the sum of the first n terms. Okay, I'm going to move over here and do B. In B, they tell us that A is 5 and R is 4. Go ahead and try it yourself. Press pause, try it yourself, and then check back here to see how you did. All right, again, I'm just going to take this general equation and I'm going to sub in what I know. I'm looking for the first 10 terms. So I actually know I'm going to sub in A equals 5, R equals 4, N equals 10. So the sum of the first 10 terms is 5, and then in brackets, 4 to the power of 10 minus 1. And in the denominator, I've got 4 minus 1. Simplify in your calculator. 4 to the power of 10 minus 1 changes our numerator to 5 times 1,048,575 all over 5. Sorry, over 3. Again, in your calculator, you get your final answer of 1,747,625. Sum of the first 10 terms of the geometric series. All right, it's just applying the formula, plugging things in the right way. And in the subsequent examples, we'll find out that you can use the formula even if you have not this exact information. So in example 3, we are going to determine the sum of the geometric series given the first 3 terms and the last term. Now we know if we're going to be determining the sum that we're going to be using this formula, but I don't have enough information because I don't have the value of n. I don't know how many terms are in this sequence. Now this sequence is pretty short. It's not that difficult to determine how many terms are here between 32 and 1 over 8 if you're dividing by 2 each time. Okay, which means we know the common ratio is multiplying by 1/2. But you go from 8 to 4 to 2 to 1 to 1/2 to 1/4 to 1/8, and you'd be there. Okay, but what if it were a much longer series? You'd need a better way to figure this out. So what we're going to do is we're going to take what we know. So the first term is 32. We know that the common ratio is 1/2, and we know the value of the last term. Okay, it's 1/8. Now we're going to take the formula for generating the last term in a geometric sequence, which is T sub n equals A times R to the power of n minus 1. Of course, you have that memorized. And we're going to sub in what we know. We know that T sub n is 1/8. We know the first term is 32. We know the ratio is 1/2. And up here we have n minus 1. All right, we're going to solve this the same way that we did before. We're going to divide both sides by 32. On the right side, that's easy to see, it's going to leave us with 1/2 to the power of n minus 1. And on the left side, what happens when you divide a fraction by a whole number is your pieces get even smaller. So you're taking 1/8 of something, and you're dividing that 1/8 into 32 pieces, which means that you're going to end up with multiplying 32 in the denominator by 8. So you end up with 1 over 256. Okay, a tiny little fraction. Now, in order to solve for n, we're going to use the same strategy as we did in the previous lesson, we are going to write 1 over 256 as a power of 1/2. That means write it as a power where 1/2 is the base. So basically we need to think, what am I raising 1/2 to get 1 over 256? So I'm really saying how many factors of 2 are there in this denominator? Well, 2, 4, 8, 16, 32, 64, 128, 256. So I counted 8 factors. And you can do that on your calculator. So 1/2 to the power of 8 is equal to 1/2 to the power of n minus 1. And then a little note, since the bases are equal, comma, the exponents are equal. There's no other way to make it. If you've got the same base and they're equal, they must have the same exponent. So we can drop the bases altogether and say 8 equals n minus 1. Then we can add 1 to both sides. We end up finding out that there are 9 terms in this sequence. All right, so now we can take that information and we can sub in what we know into our formula for the sum of the first n terms. And this time we know we're looking for the sum of the first 9 terms. We know A is 32. We know R is 1/2. We know there's going to be 9 factors, and then we're going to take away 1, close off that bracket, and in the denominator we've got 9 minus 1. All right, you can do this piece by piece. Inside the bracket, we're going to end up with 1/2 to the power of 9 minus 1, which gets us, if I did this out, you'd be able to see it. So why don't I do it each step? I'll do an extra step here just so you can see what happens inside this bracket. 1 to the power of 9 gets us 1 over 512. Okay, tiny little fraction. And then we're going to subtract 1. But in order to subtract, I need to have a common denominator. So I'm going to express 1 as a fraction over 512, which is 512 over 512. Okay? Denominator I can reduce to 8 right away. Let's focus on the numerator though for a second so you see what happens inside this bracket. It's kind of an awkward little subtraction. But if I have 1 and I subtract 512, I'm going to be at negative 511. And I'm dealing with pieces that are 512ths of a whole. Okay, so I have almost negative 1, but I don't. I have negative 1 plus this 1 512th, this tiny little piece, okay? That's what that looks like, over 8. You can do this a couple ways. You could just do 32 divided by 8 is 4, and then multiply it by this bracket here. What you end up with after you reduce is 511 over 8. All right, so that is the sum of the first 9 terms. The first thing that we had to do was use our formula for the general term to find out how many terms there were, and then take that and sub it in with the rest of our information into the formula for the sum of the first n terms. Okay, let's try that again with another example. All right, I know I'm going to be using these 2 formulas that I've written here, and I'm going to now collect some information that will be subbed in to both formulas. First the one for the general term, and then for the sum of the first n terms. We know that in this series, a is 1. Common ratio is -3. 1 times -3, -3 times -3. And we're told that the last term is -243. All right, so we'll sub those into our formula for the general term. We have negative 243 on the left, and on the right we have a first term of 1 times negative 3 to the power of n minus 1. So left side stays negative 243. On the right, we have anything times 1 is itself, so we have negative 3 to the power of n minus 1. Now it's a case of representing negative 243 as a power with negative 3 as its base. Okay, you could probably do this in your head. You probably have memorized that 3 to the power of 4 is 81, and one more factor of 3 will get us 243. Conveniently, it is an odd number, which makes it true that it will be still a negative. Okay, an odd number of negative factors results in a negative product. And that's equal to our right side. If the bases are the same, then the exponents are the same. Add 1 to both sides, n equals 6. Put a little box, and carry on. So now we know we're finding the sum of the first 6 terms. We have a value of a, which is our first term in the series. That's 1. So really I don't need to write it at all, but I'm going to sub it in anyway. It's our numerator. Inside the brackets we have r, which is negative 3. Bracket that. It's going to be to the power of n, which is 6. Then I'm going to subtract 1. Close off that bracket. In the denominator, we have r minus 1. R is negative 3. So I get negative 3 minus 1. All right, anything in the numerator, anything times 1 is itself. So I just have negative 3 to the power of 6. Well, I know that, you could get out your calculator for this, but I know that negative 3 to the power of 5 is negative 243. So I just need one more factor of 3. Which brings us up to 729. And then I'm going to take away 1. And I know this is positive 729, because there's an even number of negative factors. 729, take away 1 in the numerator gives me 728. In the denominator, we have negative 3 minus 1, that's negative 4. This reduces to negative 182. So the sum of the first 6 numbers, I guess the sum of all of the terms in this series, because it only has 6 terms, is negative 182. Example 4, real world application tennis tournament. A tennis tournament has 128 entrants. A player is dropped from the competition after losing 1 match. So single elimination tournament with 128 entrants. Winning players go on to another match until the tournament ends. They go on and on and on, and people get knocked out after 1 loss. What is the total of number of matches that will be played in this tournament? So let's think about why this can be represented by a geometric series. If you're starting with 128 entrants, and let's say people get knocked out round by round, well then how many games, how many matches are there in round 1? It takes 2 entrants to play a match. So in round 1 there are 64 matches in round 1. So what we're saying is, and after those are played, half of the players are going to be eliminated, right? Half will win and half will lose. 1 will win at each court and 1 will lose at each court. So in round 2, there are only going to be 64 entrants remaining, and they'll play each other in some, according to some schedule, and there will be 32 matches in round 2, okay? And then after that, half of them will get knocked out. There will only be 32 entrants remaining, and there will be 16 matches in round 3. So you can see how this is going to be a geometric series where the common ratio is 1/2. Okay? And I think we can probably figure out our last term in this series. If we play a certain number of rounds, how many people are going to be left at the end of the tournament? Well, in the last round, there will be 2 players. They'll play each other, and one of them will win. The other one will go home. So our final term is 1. Okay, I'm going to clear this, and then I'm going to record some of the things that we found out together. You know what, maybe I'll just leave all this. We have an initial value of 64 because there are 64 matches in round 1. We have a common ratio of 1/2 because half of the players are eliminated. We're going to divide by 2 each time. And we have a final term of 1. So we cannot go directly into our sum of terms formula because we do not know how many rounds there are. We don't know the value of n. So again, we'll start with formula for the general term of a geometric series or sequence, which is a times r to the power of n minus 1. We'll sub in what we know. The nth term is 1. A is 64 times 1/2. Don't need this. I don't need this big square bracket here. 1/2 to the power of n minus 1. Okay, divide both sides by 64. On the left, I have 1 over 64. On the right, I have 1/2 to the power of n minus 1. In order to figure out what n is, I need to represent 1 over 64 as a power of 1/2, a power with a base of 1/2. So basically, how many factors of 2 are in 64? Well, 2, 4, 8, 16, 32, 64. There are 6 factors. Then if the bases are equal, the exponents must be equal. So 6 equals n minus 1, add 1 to both sides, n equals 7. Take that information, plug it in our formula for the sum of the first n terms, which is s sub n equals, in the numerator, a bracket r to the power of n minus 1 bracket over r minus 1. There is a little, it's a bit tricky to memorize both of these, partly because this one is a times r to the power of n minus 1. And this one is a times r to the power of n minus 1. You can say it the exact same way, but they're actually very different, okay? For the general term, n minus 1 is the exponent. For the sum of the first n terms, n is the exponent, and then you're going to subtract 1, okay? Try very hard to keep that straight. At any rate, sub in what we know. We're looking for the sum of the first 7 terms. The first term is 64. R is 1/2. We're going to raise that to the power of 7. Then we're going to take away 1. In the denominator, we have r, which is 1/2 minus 1. All right. So in the top here, we reduce to 64. 1/2 to the power of 7 is 1 over 128. And we're going to subtract 128 over 128. So we end up with negative 127 128ths. Very close to negative 1. 1 128th greater than negative 1. Okay? Close that off. In the denominator, we have the same kind of thing happening. We've got half, take away 1. That's going to leave us with negative 1/2. Again, I'm using fractions as long as I can because I see that things kind of cancel out easily. Dividing by 1/2 is the same as multiplying by 2. So I could say that this is 128 times negative 127 over 128. Well, if I have 128 here and 128 here, those guys cancel out. Maybe I'll write that step. Dividing by 1/2 is the same as multiplying by 2. Okay, now I have a value in the numerator that's being divided by 128 and multiplied by 128. I have 2 negative factors. 127. So what were we actually finding out? We were finding out the total number of matches. So this is the matches in every single round added up. It's these 64 matches added to these 32 matches, added to these 16 matches, to the 8 matches, to the 4 matches, to the 2 matches, to the 1 match. Okay? And here we go. Final statement, a total of 127 matches will be played in this tournament. All right, a geometric series is the sum of terms in a geometric sequence. It has a formula for the sum of the first n terms, using a lot of the same information that we're used to gathering, a, r, t sub n, n. And in order to get some practice with this, your problems can be found on page 408, numbers 1 through 12.